So our question is, how many of these molecules are polar? And we have the molecules of OF2, SO3, BeCl2, CCl4, and O3, which is ozone. The steps to deciding if a molecule is polar is drawing the Lewis structures, identifying the bond dipoles, and then identifying the net dipoles based on their molecular geometry. So I'm going to start out with OF, which has 20 valence electrons. And I'm going to draw the Lewis structure for that. And we start by putting the filling the outer shells with an octet. So I'm going to add 6 onto this one, add 6 onto this one. So far we've used up 1, 2, 3, 4, 5, 6, 7, 8 pairs for a total of 16 electrons. So we have 4 left over, which go on the center atom. And I'm going to draw a partial negative charge on the 2 fluorine atoms since they're more electron negative than oxygen, and a partial positive charge on the oxygen. And because these are more electron negative, the electrons are going to have a bond dipole that flows towards them in opposite directions like this. And because the oxygen has 4 domains on it, it's going to have a tetrahedral domain geometry, so it's going to look something like this in reality. And as you can see, the bond dipoles in the molecule flow this way, creating a net dipole in this way. So since all of the domains are not the same, it's going to flow outwards. The electrons are going to flow outwards, creating a net dipole going south like this. So it's going to be a polar molecule, again, due to the 2 different lone pairs on the oxygen. And the bent molecular geometry does not cancel out. So here is the Lewis structure for SO3. The first thing we're going to check is to make sure that they all have an octet. Just has 1, 2, 3, 4 pairs to make 8. This is 1, 2, 3, 4 pairs to make 8, and 1, 2, 3, 4 pairs to make 8. So all the oxygens are good. Now S has more than 8 electrons around it, but because it is on the 3rd row of the periodic table, it's acceptable to violate the octet rule in this situation. Now I'm going to draw a partial negative charge on all of the oxygens here, because they are more electron negative than the sulfur. And I'm going to draw the bond dipoles go towards the more electron negative, which is the oxygen. And the molecule is gonna, in actuality, look something like this. It's a trigonal planar. And because this sulfur has no lone pairs on it, all 3 domains are same. So I'm going to show you. They all go in equal directions. The electrons all go in equal directions away from the sulfur, so it's actually going to be a non-polar molecule since all of the directions of the bond dipoles cancel out. So I'm going to go to the next one, which is BeCl2, and here's the Lewis structure for it. It is 16 valence electrons, and we're going to check the octet rule. On every atom, you can see that Cl right here has 1, 2, 3, 4 pairs, which is going to give you 8, so that's okay. This one, same thing, 1, 2, 3, 4 pairs, gives you 8. Now, Be is one of the, it only has 4 electrons here, because it has 2 pairs, but is one of the elements that can actually take on less. I think it's like Li, Be, and B, hydrogen, can take on less, so this is actually acceptable in this case. Now, chlorine is a lot more electron negative than Be, so I'm going to draw partial negative charges here, and then we can show the dipole going with equal strength towards the Cl since they're more electron negative. Now B has 2 domains, which means it's going to have a linear domain geometry, and it has no lone pairs, and only 2 domains, so it's going to also have a linear molecular geometry. Now, because these bond dipoles are situated directly 180 degrees apart in opposite directions. They're actually pulling each other both in the same force of opposite directions. So it's going to be a non-polar molecule in the end there. And I'm going to move on to CCl4, which is 32 valence electrons. We're going to check the octet rule for this one first. So you can see this has 1, 2, 3, 4 pairs. 4 times 2 is 8. This one has 8 electrons around it. This one has 8 electrons around it. And this one has 8 electrons around it. So that's okay, that's okay, that's okay. Carbon is good. It has 1, 2, 3, 4. Also has, so all these, none of them violate the octet rule. If we make sure that we're using all 32 valence electrons, we count the pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 16 times 2 is 32. Minus 32, 0. Okay, so the Lewis structure is correct. I'm going to draw a partial negative charge on the CLs, because if you look at the periodic table, Cl is more electron negative than carbon here. So carbon and Cl are gonna have equal bond dipoles that go towards the Cl, again due to their higher electron negativity. And it looks like a square planar formation here, but because of the 4 domains, it's actually gonna have a tetrahedral domain. And since none of the domains are lone pairs, it's going to have a tetrahedral domain and molecular geometry. So I'm going to draw it in a normal space for you to see here as best as you can in 2 dimensions. And you can see all of the atoms in a tetrahedral domain and molecular geometry are situated exactly 90 degrees apart. So they're actually, it may not look at it like this, but they're actually pulling equally in all opposite directions of C, and there's no lone pairs. So due to all the domains being the same and it pulling in equal opposite directions, this is also going to be a non-polar molecule. Okay, so that's not one. So I'll move on to the final one, which is ozone O3 down here. It has 18 valence electrons, but first we're gonna check out if it fits all the octet rules. So this one has 4 pairs, 1, 2, 3, 4 pairs, so it's 8 electrons. This one has 4 pairs, so it's 1, 2, 3, 4 electrons, so that's another 8. And this one only has 6, so we're actually gonna take one of these off right here and make a double bond for ozone. And then we can count the amount of pairs to make sure we're using all the valence electrons. So it's 1 pair, 2 pair, 3 pair, 4 pair, 5 pair, 6 pair, 7 pair, 8 pair, 9 pair. So 9 times 2 is 18. Subtract 18 from that, 0. Okay, you're gonna notice I'm not going to draw a partial negative or a partial positive for this one because the electron negativity of O is equal to the electron negativity of O. So there's no bond dipole. So you might think that that makes it a non-polar molecule, but actually the lone pair domain here is gonna make it polar. And I'll show you. It has 3 domains, so it's gonna be trigonal planar. So it's gonna look something like this. Now, even though there's no bond dipole, the lone pair right there is gonna pull the electrons more affinity to the central atom with the lone pair. So this actually is going to be a polar molecule. So if we go back to the beginning question of how many of these molecules are polar, well, right here we said that OF is a polar molecule because it has 4 domains, but 2 of them are lone pairs, and it's pulling away, so it's the net dipole going down right there, so that's a polar molecule. SO3 is not a polar molecule because all the bond dipoles are going in equal and opposite directions away from each other, and it has no lone pairs, so all the domains are same. So this one is non-polar. We said BeCl2 is non-polar because, again, they're pulling it in ZZC, they're pulling in opposite directions, so the dipoles are going to cancel out, making it non-polar. So that's not one. And then ClCl4, CCl4, same thing, pulling in opposite directions, no lone pairs, all the same domains. So it's going to be non-polar molecule. And then ozone was the weird one. It has no bond dipoles and no like partial negativity or positivity, but the lone pair in the ozone is going to make it polar because it is one domain that is it's different from the other two domains between the two bonds. And even this bond right here doesn't matter because the actual, this is just the Lewis structure, but the actual molecule has resonance. So this is simultaneously happening, so there's actually like 1 and 1/2 bonds on both sides of these. So we said that that one is also polar. So only 2 of these are polar, and that's going to be OF2 and O3. Some common mistakes that people may make, I know I've made, is that you might think that O3 is nonpolar because there's you would assume that O has no electron negativity, like difference in electron negativity, so it's immediately polar. Alright, O electron negativity equals O's electron negativity. And that's going to be all. I hope that wasn't too mind-numbing or anything. Thank you.